So yeah, so I'm going to be talking about structure versus randomness and complexity theory. So yeah, somehow I guess the kind of inspiration for this talk is this sort of like phenomenon in various areas of mathematics, such as combinatorics and number theory, where dichotomies between structure and randomness play an important role. And in terms of references are found online discussing this kind of structure randomness paradigm. There's Tao's ICM survey and Semireddy's theorem from 2006, or his Fox tutorial on structure and randomness in combinatorics, or the Sarnak's Mahler lecture on randomness and number theory. So there's various sort of discussions of how this kind of paradigm works in areas such as combinatorics and number theory. And the essential idea is that if you're trying to prove a result for all objects of a certain type, say graphs or numbers or sets, then what you're trying to prove might be true for different reasons. So it might be true in case the object is very structured in some sense. And it might be true also if the object is random. So it's true for different reasons. And in certain cases, you can show sort of a structure randomness dichotomy, where if the object isn't structured, then there's sort of some sort of statistical law that governs a lack of structure. And this can be exploited to show what you want to show for those objects. That's what a structure randomness dichotomy is. So that's at a very, very high level. And there are several examples of this kind of phenomenon being used in proofs in these areas. So for example, there's Roth's theorem on three-term arithmetic progressions and dense sets and dense subsets of 1 to n. And this Green-Tao theorem on arithmetic progressions in primes. And there's many, many, many other examples. And what I'd like to do in this talk is to explore a similar viewpoint on structure versus randomness in the context of computational complexity theory and complexity lower bounds. And of course, it's not surprising that such a viewpoint will help in complexity theory, because complexity theory also deals with very unstructured objects, Boolean functions, and questions about their complexity. The point is really to kind of show some kind of concrete results and how this sort of paradigm is manifested when trying to prove these results. So I'm going to be discussing three examples drawn from my own work. So let me just kind of go over them slowly, and then I'll give you like a plan of the rest of the talk. So the first result from just a couple of years back is the result of Igor Oliveira, which is about generating primes. So the result states that there's a sub-exponential time randomized algorithm that for infinitely many n generates a fixed prime of length n. So there's a randomized algorithm running at time 2 to the n to the little o 1 that for infinitely many n generates a fixed prime Pn of length n. The second result is a result about complexity lower bound. So this result says that MA, which is the complexity class, which is essentially the randomized version of NP, it's NP, but where the proofs are not deterministic polynomial time, but rather randomized polynomial time. That this class, or promised problems in this class, don't have Boolean circuits of size n to the 100, or of size n to the k for any fixed k. That's the second result. So it's a low bound result. And the third result is the result in metamathematics of complexity theory, or proof complexity, which is kind of an unconditional result saying there are no efficient propositional proofs of certain kinds of proof complexity low bounds, or proof complexity low bounds for the so-called random truth table tautologies, which are certain natural tautologies, propositional tautologies, for which one is interested in showing proof complexity low bounds. That even these proof complexity low bounds exist, there's no efficient way to establish them propositionally. That's what theorem 3 is saying. And as I discuss these results in more detail, it'll be clearer precisely what I mean in each case. So these are quite different results on the surface. I mean, the first result is an algorithmic result. The second one is a low bound. The third is a mathematical result, which is sort of asserts the unprovability of a low bound. And they're also drawn from different areas. The first one from explicit constructions, the second one from conditional complexity, and the third one from proof complexity. But the interesting aspect is that the proof template in all three cases are essentially the same. So I mean, that's the reason that I'm kind of discussing them together. The proofs of these results all use a dichotomy between structure and randomness. So I'm quite interested in the sort of like this dichotomy between structure and randomness as a proof method. That's partly my motivation. But I'm also interested in it more broadly as sort of a fundamental phenomenon that we need to understand better. So yeah, I'll be kind of discussing both of these aspects. So here's how the rest of the talk will look. So I don't want to assume too much about a knowledge of complexity theory. So I'm just going to give first just a few slides with just kind of a brief explanation of the concepts I'll be talking about. And then I'm going to discuss sort of each result, spend about maybe 10 minutes for each result, giving you the context and the motivation for showing that result, giving you the statement of the result, and then a sketch of the proof, sort of foregrounding the role of structures as randomness in the proof, and then saying a little bit about features of the result that arise from the use of structures as randomness. And these aren't always desirable features such as non-constructivity. So I'll be doing this for each of these three results. And at the end, I'll give some perspective. So I'll discuss structures as randomness as a proof technique, and then also as a phenomenon that's important to understand. And at any point, if anything is unclear, feel free to interrupt me. I mean, it's maybe a bit ambitious in trying to cover quite a lot of territory, but I'm not going to go very deep into any result. I mean, the main point is to see sort of the conceptual similarity between the proofs of these various results. Okay, so first, just a kind of a brief primer on complexity theory. So yeah, so many of you will be familiar with this, but yeah, I can just reiterate. So these are the kind of complexity classes that I'll be discussing. So here it is uniform complexity theory, very interested in computing a Boolean function by kind of a fixed program by a Turing machine. And P is a class of languages that compute on polynomial time. NP is the class of languages compute on non-termistic polynomial time. MA is analogous to NP, but we have randomized polynomial time verifiers rather than just deterministic polynomial time verifiers. Polynomial space, class of languages deciphered in polynomial space, and X is deterministic exponential time, languages deciphered in deterministic exponential time. And there's sort of an easy sequence of inclusions between these classes. So P is contained in NP, which is contained in MA, which is contained in P space, which is contained in X. These are all very easy to see. And from the time hierarchy theorem for deterministic time, we know that P and X are different. So there's some consecutive pair of clauses here which are different, but we don't know which. And in fact, for every consecutive pair here, we believe them to be different, except in the case of NP and MA, for which there's some evidence that they're the same class. So for any class C of languages, the Boolean functions, co-C will denote the class of complements of languages in C. So these classes P, P space, and X are all closed in the complement. So co-P equals P, co-P space equals P space, co-X equals X. These are all very easy to see for deterministic classes. For NP, we don't believe there is closed in complement. And in fact, the question of whether NP equals co-NP is a major open question, and we believe the answer to be negative. So this is essentially what I'll be using about a uniform complexity theory. And then there's non-uniform complexity theory, where rather than trying to compute a Boolean function using a fixed program, you think of the Boolean function as a sequence of Boolean functions on n-bit inputs. And you look at how to compute each n-bit Boolean function by Boolean circuits. Where the Boolean circuit is kind of like this fixed kind of Boolean network, which computes that function f on n-bit inputs. And you look at how quickly the size of the smallest Boolean circuit needed to compute the function grows with the input length to the function. So if S is a size measure, and S of n is a function on where n is the input length, then size of S is a class of languages that are accepted by Boolean circuits of size at most order of S of n. By playing off kind of uniformity versus non-uniformity, we get lots of interesting complexity questions. So for example, NP, whether NP has polynomial size circuits is a major open question. So also whether exponential time has polynomial size circuits. And there's also this notion of advice, which we can use to kind of interpolate between uniformity and non-uniformity. So, I mean, non-uniformity is kind of on the surface more powerful. And we'd like kind of a notion that can kind of smoothly interpolate between pure uniformity and full non-uniformity. So given a uniform complexity class C, we have the class C/A, which is the class of languages accepted by a machine deciding a language in C, but given A of n bits of advice. So there's a separate tape, the advice tape, on which you have a string which is of length A of n and depends only on the input length n, not on the input. And yeah, and that's sort of the computational mechanism for your language. So if A is 0, if there's no advice state at all, that's just the uniform class C. While if A is sort of, if C is a polynomial time class and A is polynomial, then this gives you the polynomial size kind of non-uniform version of C. So for example, size of poly is equal to P slash poly. It corresponds to uniform class C with polynomial number of bits of advice. And there's kind of a result called the Karp-Lipton theorem, which relates sort of inclusions of uniform classes and non-uniform ones to collapses of uniform classes. So for example, there's a Karp-Lipton theorem for polynomial space due to Babaifort Lund and to Nissan, which says that if polynomial space has polynomial size circuits, then polynomial space collapses to MA, which is, as I said before, is a randomized version of NP, which is a very surprising collapse. So this is sort of suggestive. It sort of indicates that polynomial space is unlikely to have polynomial size circuits. So yeah, that's just a very brief intro to kind of what I need about uniform and non-uniform complexity theory. And what do I mean by structure versus randomness? So we're going to be using kind of the structure versus randomness dichotomy in a fairly simple way in the examples in this talk. By the structure case, I'll mean that there's some language L which we believe to be hard. So for example, a language, let's say polynomial space complete or otherwise hard. So language which we don't believe is easy, but has efficient algorithms and circuits. So it's kind of surprising inclusion that L, which is P-space complete, is either easy non-uniformly or easy uniformly. And the random case, well, there's if we're not in the structured case, in the unstructured case where L doesn't have efficient algorithms and circuits, but just the lack of structure is not always kind of something that's useful. Quite often we need something more, some sort of statistical properties that we get from the lack of structure. For that, we'll use kind of the classical connection between circular low bounds and pseudorandomness. So there's a beautiful theory of pseudorandomness, which stems from the work of, in complexity theory, from the work of Nissan and Vigdison, Vigdison and others. So for example, if this language L doesn't have efficient algorithms, this implies the existence of a pseudorandom generator G, which is a function which takes R of n bits to n bits, and it's computable in exponential time. So it's computable in time 2 to the order R of n. And this generator fools every efficient algorithm or circuit A on n bits. And by that, I mean that the algorithm A can't really distinguish a uniformly random input from the output of the pseudorandom generator on a random seed, right? So the probability that A accepts on a random n-bit input is approximately the same as the probability that A accepts on G of Z for a random R of n-bit Z. So what's interesting about this is that it sort of transforms a complexity low bound to something that's algorithmically useful, in the sense that from a complexity low bound, we get this objective PRG, which means you can kind of reduce the randomness required by a randomized algorithm. So if a randomized algorithm running a polynomial time used n bits, now you can make do with R of n bits of randomness and apply the generator and use that as a source of pseudo-randomness to simulate the randomness that you had before. So from a complexity low bound, we get something algorithmically useful. And that's kind of intuitively the reason why this turns out to be productive. Okay, so that's kind of a brief discussion of structures of randomness. So let's get to the first result, generating primes. So here, the context is explicit constructions of various kinds of objects, combinatorial or otherwise. So for many interesting mathematical objects, such as prime numbers, Ramsey graphs, graphs that don't have a large clique or independent set, or error correcting codes, we know that random constructions work in the sense that a randomly chosen number between 1 and n is going to be prime with a significant probability, at least like 1 over log n, and a kind of a randomly chosen graph with kind of like constant edge density is going to be Ramsey with high probability. A random set of code words is likely to form an error correcting code. So random constructions work. But we would like fixed constructions of such objects. We'd like constructions which generate a fixed object of this type, an explicit construction. So in general, the goal is that given a property Q, such as primality or Ramsianus, we want to give a deterministic polynomial time algorithm, or at least sub-exponential time algorithm, that an input 1 to the n outputs an object in Q of size n. So we are given as input the size of the object we want to output in unary, and we want to output an object in that size. And for properties such as primality and Ramsey, we seem quite far from achieving this goal. In the case of Ramsey, there's a lot of interesting recent work on randomness extractors, which gets us closer to this goal, but still doesn't give us like optimal Ramsey graphs. And for primality, we seem even farther away. So the best known deterministic construction for primality runs in time approximately 2 to the n over 2, little n over 2, where n is the length of the prime you want to generate. Notice that there's kind of an obvious kind of naive construction running in time 2 to the n times poly n, where you just sort of enumerate all possible numbers of length of bit length n, and then you check for each one whether it's prime using deterministic primality test and output the first one. So that takes time 2 to the n, but we want to beat that significantly. And the best known is 2 to the little n over 2. And there was a Polymath 4 project, which was sort of spearheaded by Kroot, Helfgott, and Tao, which tried to beat this bound, but didn't get, I mean, they proved lots of interesting things, but they failed to get an unconditional improvement of this deterministic construction. 2 to the little n over 2 is still the best construction known. Okay, so we're going to kind of relax the goal somewhat. So the original goal was to kind of compute this object deterministically. We are going to think about certain kinds of randomized constructions with stronger properties. So yeah, as we discussed, random constructions work for properties such as primality and Ramsey, but there the object constructor depends on the randomness of the algorithm. So for example, you kind of generate a random graph of certain edge density, and then you output that graph. So clearly the object that you output depends on randomness that you've used. And that will seem natural. I mean, why would you use randomness if it's not going to influence your choice of the output? Well, I mean, we are going to consider this possibility where somehow the randomness is useful, not because it generates kind of like an output space of high entropy, but somehow because it helps you find the object more efficiently. So we're interested in kind of a slightly strengthened notion of random construction, which we call a pseudodeterministic construction. This was first defined by Gatt and Goldwasser. And a pseudodeterministic construction for property Q is a randomized algorithm that, given 1 to the n, outputs a fixed object in Q of size n with high probability. So there's kind of a canonical object of size n that you want to output. And you want to output that object with high probability, but you want to do it as efficiently as possible, ideally in polynomial time, but certainly kind of sub-exponential time. And Gatt and Goldwasser ask if there's a polynomial time pseudodeterministic construction for primality. And the known number theoretic results don't seem to lead to any significant improvement in the best deterministic construction. So if you look at the Polymath 4 project, that seems to give a slight improvement to 2 to the cn for some constant c that's slightly smaller than half, but at least the methods in that project seem to yield only that. And it's unclear how to do much better using number theoretic methods. So what we do is use purely complexity theoretic techniques to get an improvement. So and the result that we go all over is that there's a randomized algorithm running in time 2 to n to little o of 1. The little o of 1 can even be 1 over log n, or something even smaller than that. That for infinitely many n, so this is the caveat, so it doesn't work for all n, but only for infinitely many n, generates a fixed prime Pn of length n with high probability on input 1 to n. So in terms of the time complexity, this significantly improves on the best deterministic algorithm, but it does have the caveat, the issue that it works for infinitely many n rather than for all n. And somewhat surprisingly, the method is purely complexity theoretic and only uses standard facts about primes, almost elementary facts. So the prime number theorem, which says that omega 1 over n fraction of n bit numbers are prime, and efficient primality tests. The fact that primality isn't key. In fact, for the specific result of proof I'll be discussing here, we only need the primality is in BPP, which is already known from Miller, Rabin, and Solvay-Strauss and primality tests. So we'll just be using these facts or primes. And here's the kind of like a sketch of the proof. So we're using the structure of the randomness paradigm. So what we're going to do is we're going to take a language L, which is a special p-space complete language, which is kind of given in work of Trevisan and Vadan. So a p-space complete language has certain special properties, which I'm not going to go into in too much detail. And now we have sort of the structured case and the random case. So the structured case, to remember, is that L is sort of surprisingly easy. So L is in BPP. So it's a p-space complete language, which you don't expect to solve in BPP. The structured cases is an unlikely case that L is in BPP. And in that case, the argument is not too hard. So if L is in BPP, because L is p-space complete, it means that all of polynomial space collapses to BPP. And then the intuition is that, well, I mean, you can easily solve primality in polynomial space, and you can in fact find the first prime of a given length in polynomial space. So if p-space equals BPP, you can also do that in probabilistic polynomial time. You can kind of like find the first prime of length n in probabilistic polynomial time and output that. And that will be a pseudo-deterministic polynomial time construction. When more formally, you kind of consider this language where you kind of like encode 1 to the n and I, and you want to know whether the ith bit of the lexicography's first n bit prime is 1, whether that language is in polynomial space. So from the fact that polynomial space equals BPP, it's in BPP. And then you can kind of like, by solving this language for each I between 1 and n, you can find out what the bits are of the lex first prime, and you can output that prime. So, so that's sort of like the simpler case. The random case, yeah, we know that L is sort of like unstructured. It's not in BPP. And then we use sort of the connection between low bounds and pseudo-randomness that I mentioned before. And there's an exponential time kind of computable PRGG for any epsilon greater than 0 with seed length n to the epsilon that fools primality. And that's because primality is a polynomial time computable predicate. We know it's polynomial time computable. It's an efficient predicate. And therefore, from kind of like a low bound from L not in BPP, we get a PRG that fools this test. So, but what does it mean for the PRG to fool this test? It means that the probability of a number being prime is pretty close to the probability of an output of the PRG being prime. And since the probability of a number being prime is like 1 over n, this means that like with probability approximately 1 over n over outputs of the PRG, that output is prime. And in particular, there's at least one output of the PRG that's prime. So we can just enumerate over outputs of the PRG, and we can kind of check each one as we enumerate them, whether they're prime or not, and output the first such one, right? So this gives an algorithm which is in fact deterministic that enumerates outputs of G and prints the first prime output. And it runs in sub-exponential time because it just needs to enumerate outputs of generator, which are the most 2 to the n to the epsilon of them, and it takes only 2 to the order n to the epsilon prime to do this enumeration. But the caveat now is that this only works infinitely often because in the structured case, we know that L is in BPP on all input lengths. In the random case, we know only that there are infinitely many input lengths on which L is hard, and so this PRG only fools primality on infinitely many input lengths n, and therefore, finally, this algorithm that enumerates outputs of G and prints the first prime output also works infinitely often. So in both cases, the structured case as well as the random case, we have a pseudo-deterministic construction. In fact, in the first case, we have a pseudo-deterministic polynomial time construction that works in all input lengths. In the second case, we have a deterministic sub-exponential time construction that works on infinitely many input lengths. Okay, so yeah, it's just the theorem again. As I said before, it improves on the best deterministic algorithm, but it does have this caveat. It works for only for infinitely many n. And also, kind of a strange feature of using the structure as a randomness paradigm is that the algorithm is non-constructive. So we know that there's an algorithm that works, but we can't come up with kind of the code of a fixed algorithm that works, which is kind of like a strange situation, especially when you have an algorithmic result. And this corresponds somehow to a lack of knowledge about whether the structure of the random case holds. we know that at least one of these two cases holds. So just one bit of information about our world. Is our world structured or is it random? But we don't know that. And because we don't know that, it's not obvious to come up with a fixed algorithm that works. And in fact, for this theorem one, by a lot of additional work, you can make the algorithm constructive, but there's a result which is also zero error, where you never get an erroneous answer, we never get a different prime, that we prove in this paper, where we don't know of a constructive algorithm.
Rahul,
yes?
can I ask a question?
Sure.
Yeah, why can't you run them both in parallel, both algorithms? And, up to the time allotted, and one of them will generate a prime for you.
Yeah, yes, so the problem is with this notion of pseudo-deterministic, where you only know that high probability it'll work. So it's not clear how to amplify it. So it might be that like you might get something with probability less than half. I mean, if you have two candidate algorithms that are pseudo-deterministic, it's not clear how to combine them to get like an algorithm is always pseudo-deterministic.
So the first one, the structured case, you get the probability only with some polynomial.
Or like smaller than half. Yeah, I mean, you might get something like, which is sort of, so getting something as close to one, you might get something that's smaller than half, close to half.
Can you say again what you said at the end about the zero error construction?
Oh, yeah. So the theorem whose proof I just discussed, so that's a randomized algorithm that generates a fixed prime with high probability. But then there's a question, what happens on other computation paths when you're not generating this fixed Pn? Can you generate other primes, P prime, P out prime, and so on? Or should it be the case that you always only generate this fixed prime Pn? So if you always generate either the fixed prime Pn or you give up, you say you don't know, that's a zero error algorithm. Well, a bounded error algorithm is one where you might generate other primes as well. So the argument I just gave gives you a bounded error algorithm, but you can in fact get a zero error algorithm as well by using an additional idea. And in that case, we don't know how to make it constructive. Any other questions? Okay, so I'll move on to the second result. So this is kind of circuit low bound. Reed, how am I doing on time? I don't have a what's right here.
I think you have a half
you're
hour.
doing well.
Yeah.
You have at least half an hour.
Okay, okay, good. Okay, so so the second result is about kind of circuit low bounds. So yeah, I mean, it's of course like the major challenge in complexity theory to show, for example, that NP does not have polynomial Boolean circuits seems a challenge far out of reach. A simpler sort of question to attack is to kind of rule out linear size circuits for NP. And even that we don't quite know how to do. In fact, the best known low bound for NP is close to 5n for circuits over the De Morgan basis. So one could sort of like ask, well, I mean, okay, the best low bound we have for NP is 5n, which is very good. But what's the smallest complexity class C for which we can show superlinear size low bounds, or even low bounds of the kind n to the 100 or n to the k for some fixed constant k. So this is something that's been kind of studied for a while. So Kannan, in fact, nearly 40 years ago, got a superlinear low bound for NP to the NP for sigma 2, we use NP to the NP. And what we get here is kind of such a low bound for MA, the randomized version of NP that I discussed before, or more precisely for MA with just a bit of advice. And under derandomization assumptions, we believe that MA equals NP. I mean, of course, like we only know how to do derandomization under circuit low bound assumptions, so that's a bit circular. But at least we believe that MA is close to NP, while with sigma 2p it's probably not. So let me just define MA again clearly. So there's a class of languages L for which there's a polynomial time randomized verifier V. So a verifier V that uses randomness, such that if X is an L, then there is a W, a certificate of size polynomial in X, such that the verifier V accepts a probability at least 2/3, and you can amplify this to something close if X is not null, then for every candidate certificate, the verifier rejects with high probability or alternatively accepts with low probability. So MA is sort of a uniform class, and if we allow the verifier just a single bit of advice that depends on the input length X, so we have an advice state and we just give on that advice state a single bit of advice, then we get the class MA/1, MA with one bit of advice. And what I showed, and this was quite a while ago, is that for every constant K, MA/1 does not have circuits, Boolean circuits of size n to the K. So the order of quantifiers is important here. I mean, if there was a language such that for all K didn't have circuits of size n to the K, that would be a superpolynomial low bound for MA, and that would also imply a superpolynomial low bound for NP. But the point is here that the language depends on K. So for every constant K, there is a language LK, which is MA/1, which doesn't have circuits of size n. So it's a weaker result than superpolynomial low bound. Okay, so here we're going to be using a very similar sort of structure, randomness kind of dichotomy. I mean, like either the world is structured in the sense that there's some like hard language, a piece-based complete language that has small circuits, or it's unstructured. In fact, we want to need the random component here, just structured versus unstructured. And yeah, let me just sort of like sketch the argument again. And I mean, I don't expect all kind of this to be followed, but just get an idea of how the proof works. So the structured case is that L, the special piece-based complete language, has polynomial size circuits. And I mentioned before that, so if L is in polynomial size, then because L is piece-based complete, it implies that all of polynomial space is in polynomial size. And there are these Karp-Lipton theorems which give you uniform collapses based on non-uniform simulations. So if P-space is in polynomial size, the Karp-Lipton theorem for polynomial space implies that P-space equals MA. And then you can just use the fact, which can be easily shown unconditionally, that polynomial space has languages not in size n to the K for any fixed K. That's a simple diagonalization. So we also get that MA is not in size n to the K. So the structure case, as in the previous example, it turns out to be relatively easy to analyze. It's sort of like the random case is a little bit trickier. So the random case here is just the unstructured case. L doesn't have polynomial size circuits. Well, what does it mean? So there's some sort of like kind of optimal circuit size for L. So there's some function S of n, which for each n tells you the best kind of circuit size for L. So, and that's going to be super polynomial. It's not going to be polynomially bounded because L is in size poly. So there's some super polynomial function S such that L is in size S and L is not in size S minus 1. And this is the optimal circuit size for L. So now what we do is we sort of like, we have kind of an upper bound and lower bound, right? I mean, just kind of like, yeah, just from the fact that these optimal circuits, we know that L is in size S and we know that L is not in size S minus 1. So the fact that L is in size S, we can sort of use sort of a parametrized version of the Karp-Lipton theorem. So the Karp-Lipton theorem says that if L has polynomial size, then P-space collapses to Merlin-Arthur polynomial time. And you can sort of like scale that, parameterize that to show that using the properties of the special P-space complete language to show that if L is in size S, then in fact LA is an MA time polynomial in S for any S, essentially. So that's now kind of a uniform upper bound, MA time polynomial in S. And you have this kind of non-uniform low bound size S minus 1. And now we sort of intuitively close to being done because we have a poly of S MA upper bound and an S minus 1 non-uniform lower bound. I mean, if S is sort of n to the K, then we'd be done because then you'd have a polynomial MA upper bound and n to the K lower bound. And we can sort of like try to use a padding argument to pretend that S is n to the K just by padding the input so that as a function of the new input length, S is around n to the K. So that's what we'll do. The issue there is that we don't know exactly how much padding to use because we don't know what S is precisely. So that's the reason why you don't really get kind of a uniform upper bound MA here, and instead you've got to use one bit of advice. Not go into detail about why you get one bit of advice, but think of it as just corresponding to this one bit of information about whether the structured case holds or the random case holds. That's what this one bit of advice corresponds to. Okay, so that's just pre-sketch the proof. Just kind of like a reminder of the result. For every constant k, MA with one bit of advice does not have circuits of size n to the k. So it's again the case that this low bound only works for infinitely many input lengths. So we're getting similar sort of like weakness of the result as with the previous use of structural randomness. So it only works for infinitely many input lengths rather than for all input lengths. And for a similar reason. And we also have similar kind of non-constructivity. The upper bound is non-constructive. And what does this mean? This means that like we don't really come up with a fixed advice-taking machine, which we know to be a Merlin-Arthur machine running in polynomial time, and which decides a language for which the low bound holds. We only get that there exists such a machine. We're not able to actually kind of come up with an explicit machine satisfying that property. And again, this corresponds to our lack of knowledge about whether the structured case hold or the random case hold. Because we don't know whether the world is structured or random, we're not able to get a constructive result. Okay, so that's the second example. And now I'm going to talk about the third result, which is about unprovability of low bound. Okay, so yeah, we know that in practice, circuit low bounds are very hard to prove. And then the question is, I mean, is this sort of like an indication of our kind of weaknesses as mathematicians, or is there a more fundamental meta-mathematical reason for this, explaining why circuit low bounds are hard to prove? And since the early days of complexity theory, there have been sort of many meta-mathematical frameworks trying to explain the hardness of complexity separations. I mean, there's kind of relativization, then there's the celebrated natural proofs barrier of Rasborough and Rudich, there's algebraization, so on. And I'm kind of going to be interested mostly here because I'm interested in non-uniform low bound. I'm interested in the natural proofs barrier. I'm not going to sort of explain what that is precisely, but it shows that standard algebraic and combinatorial techniques are unlikely to be able to show strong circuit low bounds. So under kind of standard cryptographic assumptions, sort of constructive algebraic and combinatorial techniques are unlikely to be able to show the circuit low bounds we want. But the natural proofs barrier is sort of, it doesn't really correspond to any kind of precise formal mathematical system. It's more heuristic in the way it works. And moreover, it is conditional. It kind of relies on the cryptographic assumption, which we believe, but it's still an assumption. And what we're interested here is whether we can give stronger unconditional evidence for the hardness of proving low bounds, of complexity low bounds of various sorts. And this is the setting we're going to be dealing with. So we're going to be dealing with the setting of propositional proof complexity. So propositional proof complexity is essentially kind of an analog to circuit complexity in the proof theoretic world. So just as in circuit complexity, we're interested in computing Boolean functions on kind of fixed number of inputs by smaller size circuits and interested in how the circuit size grows. Here we're interested in proving sequence of tautologies of a given length, of length n, by in a certain proof system. And we're interested in how the size of the proof, the shortest proof, grows with n, with the size of the tautology. I'm going to be using kind of like a slightly kind of like non-standard notion here, because I'm going to be talking about an unconditional result. I mean, there's a conditional result where these were the standard setting, but let's kind of like work for now with this setting of non-uniform propositional proof complexity, where you can think of a propositional proof system as just a relation computable by polynomial size circuits, such that a formula phi is a tautology if and only if there exists a W, a proof, that should R of phi W holds. So you should think of phi of R as being sort of the verifier for the proof. And this if and only if corresponds to the soundness and completeness of the proof system. So the if shows sort of soundness. If there's a proof, then phi is a tautology. And the only if shows completeness. If phi is a tautology, there is a proof. So that's what the if and only if here corresponds to. And we're interested in the size of the shortest proof W. And we're interested in a sequence of tautologies phi n, where say the size of phi n is n, and we're interested in the shortest proof w for phi n as a function of n. So the R proof size of phi is the length of the shortest w such that R of phi w holds, such that the proof system R proves phi. And we say that a sequence of formulas phi n has efficient propositional proofs if the size of the proof size of phi n is polynomial in the size of phi n for some PPS R. So the efficient R propositional proofs if the size of the proof is polynomial. And so we have like a notion of of proof complexity here. And then there's a question of, well, what kinds of tautologies do you want to study? Do you want to look at hardness for? And there's a natural family of tautologies, propositional tautologies, which basically say that a random Boolean function is going to be hard, that a random Boolean function doesn't have small circuit. It's not hard to see that this sort of property that given a fixed you have a random Boolean function, then you're given the truth table of that function. The property that this doesn't have small Boolean circuits can be expressed as a propositional tautology. And it's believed that these random truth table tautologies, it's kind of like a distribution of tautologies. This is believed to be a family of formulas that don't have short or efficient R proofs for any R, for any propositional proof system R. And what we're interested in is sort of
Rahul,
sorry.
Sure. So I know that this is conjecture or believed by some people for regular proof systems that are verifiable uniformly in polytime. But could you say something about the assumption that it's also true in the non-uniform case?
Yes, yeah. So this assumption was sort of studied by Rudich. I mean, Rudich has this kind of paper on superbits and demibits, and he was kind of interested in kind of versions of kind of NP natural proofs, and kind of like generalizing notion natural proofs to NP verifiability. And there he kind of makes conjecture, and that conjecture is actually equivalent to the hardness of random truth table tautologies for non-uniform propositional proofs. That's partly where it comes from. But
it's not known to be like, I mean, it's not. I mean, I don't know how believable it is or how much it's connected to other conjectures.
Yeah. So so I'm going to be focusing on this talk on this kind of distribution of tautologies, but I can also kind of ask a similar question about random CNFs. Kind of Feiger's hypothesis says that kind of random CNFs kind of are hard to solve on average, but yeah, you could also kind of conjecture, and I know people have done this like Ryan O'Donnell, Boris Barak, and they're also hard to prove. And so a similar phenomenon holds for random CNFs, but we don't quite get an unconditional result there. So I'm going to be focusing on random truth table topology. But the point is, so as you say, it's not clear whether this is true or not, but that will kind of factor into the proof. So so we ask if such proof complexity low bounds can themselves be shown propositionally. So here propositional proof systems are both a meta-mathematical framework where we kind of studying how to prove low bounds using this framework of propositional proof complexity, and they're sort of the object of study. So like what we're trying to formulate and prove is sort of a kind of a proof complexity low bound to show that some family of formulas doesn't have short output. So that's the question we're interested in. And what we can show is that there is some propositional proof system R, a non-uniform propositional proof system, such that there are no efficient propositional proofs of low bounds for R. So no propositional proof system, uniform or non-uniform, can efficiently show that random low truth table tautologies are hard for this proof system R. And I mean, as Tony suggested, one reason for this could be just that they're not hard, right? So that they're easy. So that's one possibility. But then there's also the possibility that they are in fact hard. But even in that case where they are in fact hard, it's impossible to actually prove it. That's the point. So this shows unconditionally that propositional proof systems are incapable of efficiently proving somehow very strong complexity low bounds. And of course, it's a matter of belief whether these complexity low bounds are so strong that one doesn't expect them to hold. So That's a question of belief, but yeah, that's sort of an interpretation of the result. And like how I like to think about this is sort of as a version of Gödel's incompleteness theorem for propositional proof complexity, because Gödel's theorem, which kind of says that a statement asserting its own unprovability is unprovable, the first incompleteness theorem, you can think of like a resource-bounded version of that, where what you're trying to show is that kind of statements don't have short proofs, and then you want to know whether there's kind of like a proof complexity low bound for such statements. That's like a resource-bounded version of Gödel's theorem, and that's a kind of result that we. So I'm not going to go into like a sketch of the proof similar to what we had before, because I think it's going to take too much time. So I'm just going to say something very briefly about structured case and the random case. So the structured case is the possibility that that's what Tony suggested, that in fact the conjecture that I had before is false, that in fact there is some non-uniform propositional proof system, such as random truth table tautologies for efficient R proofs. And then the theorem is more or less trivial. It just follows by the soundness of proof system. If there's an R for which these tautologies are easy, then of course you can't proof complexity low bounds for R, because such proof complexity low bounds just don't hold. But what's more interesting is the random case. So if you kind of actually believe that these tautologies are hard, then you can in fact show that they're hard to prove. And this case uses kind of techniques from pseudorandomness and kind of like ideas that were used by Rosberg and so on. So I'm not going to be able to discuss it in more detail. But it again divides up in the same way as the other cases into kind of structured case and a random case. Structured case corresponds to some surprising simulation or contradiction to something that you might believe, and the random case corresponds to a random-like situation. Yeah, so just to kind of restate the result. So the result is that there is a kind of a proof system for which there are no kind of proofs of proof complexity low bounds that are efficient. Again, this sort of this kind of the feature that follows from the proof technique, which is that there's some non-constructivity. The R that you get is not something that I can kind of show you. It's just that there exists some R which works. So we don't know precisely which R this is.
So why are you in this, why is this non-constructive? It seems like your statement before, the structured case was that some system can efficiently prove it, which would mean your random case is that no system can efficiently prove it. So why can't you exploit this for any system?
Well, because in the structured case, there exists a system that can prove it, but you don't know which one. So we don't know for which R it holds. That the proof complexity low bounds are hard to show.
Sure, but for every system R where it does hold, I mean, then it's trivial. So can't you just consider every system that can efficiently prove these and all the systems that can't?
I mean, the point is I can't really like tell you ahead of kind of like time. I can't say, but here's this R. I can say in the random case there is a fixed R that works. So I can tell you, okay, here's an R, which is actually a very simple kind of proof system, which just has resolution with some low circuit low bound axioms, and that's a system for which we can do it in the random case. So in the random case, there's an explicit R that works. It's just that when you're kind of doing this kind of either or argument, the structural randomness dichotomy, then you don't count for the fixed R, because it depends on kind of it failing for every kind of possible structured situation. I mean, the explicit system you get for in the random situation depends on it failing for every possible R in the structured situation, and we don't know a priori which R is the right one in the structured situation.
Okay, got it. Thanks.
Okay, so yeah, so that's sort of like yeah, kind of like sketches of these results. But now, kind of like would like to give perspective. I'd like to sort of just kind of reflect on these results and kind of give you some thoughts about that. So the first is about structures of randomness, the proof technique. So just as from these examples, the applications can be quite surprising. So for example, it's not clear why this sort of proof technique used in kind of complexity theoretic settings should be used for explicit constructions of primes, for instance. It does give unconditional results, which there aren't that many of in cases where we're dealing with strong complexity classes. So that, and it gives unconditional results because either the world is structured or the world looks random, and in both cases we can argue that the result holds. And in all the cases that I've discussed, it gives results that are non-constructive in some sense. And in each case, it's because we don't know whether the structured case holds or random case holds. And it's interesting to think about whether in specific cases, the non-constructivity can be removed. So I would particularly believe this to be the case for the result about primes, because yeah, we are really using very little about the primes. I mean, there should be kind of a way of using kind of stronger number theoretic information about the primes and making this result stronger as well as more constructive. Yeah, and I mean, there's certainly no result in number theory I know which only works for infinitely many n rather than much more frequently. So, so maybe the right way to think about strengthening that result is by using number theory more strongly. And for the other results, it's less clear, but perhaps in each specific case, something could be done in that respect. Yeah, and it's sort of, like when we're thinking about complexity low bounds, it often seems the complexity theory is stuck because low bounds seem so hard. And the structural randomness paradigm, or at least this perspective on it, shows that some interesting results can be obtained even when we don't have clear information about the truth of a low bound question. And I should point out that in all of these results, there's this kind of structure of the randomness paradigm is being used in a very limited way. There's only this sort of one bit of information: is the world structured or not? And in principle, one can imagine more sophisticated ways of using it, of maybe using structural randomness recursively. And perhaps more sophisticated techniques like that can prove more interesting results. So from the proof theoretic point of view, it'll be interesting to see if we can formalize this paradigm so that we can find maybe further applications of it and perhaps also understand its limits as a way of proving complexity theoretic results. And I don't want to go into it, but theorem 3, the unprovability of low bounds, in fact shows that in certain situations, non-constructive methods are inherently more powerful than constructive methods. And by constructive methods, I mean methods that can be implemented within propositional proof systems. So that's something that also follows from kind of like theorem 3 and some related results. So possibly non-constructivity is actually more powerful and we need to be using it more. Okay, so that's about structural randomness as the proof technique. But yeah, I think I'd like to highlight the perspective that structural randomness is a phenomenon that needs to be understood better in complexity theory, and that's even more important than using it as a proof technique. So what do I mean by structural randomness as a phenomenon? So questions such as what are the right notions of structure and randomness? Can we define useful notions in many different settings and show dichotomies between, so there's some natural notion of structure and a natural notion of randomness, and there's a dichotomy between them. So for example, so far as I said, we only use that the world is structured in the sense that some circuit are uniform upper bound holds, or it's not, or it's random. But you can ask, well, for a circuit class C, like an AC0, ACC0, PC0, is it structured or random? What's the right notion? Perhaps the notion of a circuit class being natural is kind of the right notion of structure, and that gives you some interesting information. You can ask for a computational problem, is it structured or random? And kind of try to exploit both. And this was done by Salil Vardhan and kind of his paper on Unconditional Study of Computational Zero Knowledge, where he looks at instances of computational zero knowledge problem and classifies them according to whether they're structured and random, and is able to show properties of computational zero knowledge based on that sort of dichotomy. So yeah, there's kind of many ways in which you could kind of think of structural randomness as being applied to given computational situation. And you can also ask, well, how hard is it to distinguish structured from random? Because certainly one of the bottlenecks in our use of it was that, yeah, we didn't know which was the case, the structured case or random case, and that led to sort of certain form of non-constructivity in our results. But maybe by actually studying computationally how difficult it is to tell if an object is structured or random, that's something that perhaps would be useful. And I point out that there's lots of recent work on the complexity of the minimum circuit size problem, where you're given a Boolean function by its truth table and you want to know whether it has small circuits or not. So that's one form of trying to distinguish structured from random, asking about the complexity of the minimum circuit size problem. The other question, well, another question is, are there simple characterizations of structure, ways of relating different notions of structure? For example, one can think in terms of stability, like if an object is close to being structured, Does that mean a related object is structured? For example, worst case to average case reductions in complexity theory, kind of substability phenomena, and you can try to kind of relate other notions of structure as well. And like finally, yeah, I mean, just sort of like speculation on whether this kind of like structures randomness either as a paradigm can be useful to make progress on long-standing open questions. I mean, yeah, my belief would be that the current instantiations of this as a proof technique are nowhere near sophisticated enough to attack such questions. I mean, after all, like our kind of division of the world into structure and random is itself somehow about lower bounds. So it's not clear how to prove like new strong lower bounds using this sort of division. But I would think that trying to understand this better as a phenomenon, I mean, trying to understand what structure and what the right notion of structure and randomness are more generally, is very likely to lead to progress, and it's perhaps even essential to making progress. Yeah, that's all. Thanks.
Okay, thank you so much. Some questions?
Do you think there's any chance of getting better results on the B versus VPP question using these methods?
Yeah, I mean, so P versus BP is closely related to low bounds, right? I mean, of course, we know that low bounds imply P versus B equals BPP, but even Kamnas and Pamela are related as well show that derealization implies certain kinds of low bounds. So, yeah, I mean, maybe separating BPP from next. I mean, a very kind of like just something fairly kind of relatively weak like that, maybe, but for like stronger derealizations, again, I would guess that, yeah. But this is just a guess. I mean, I really have no way of knowing, but yeah, I mean, I see no way of using this there.
Go ahead.
No, go ahead.
I have a question, Rahul. So thank you for the talk. And I think you made a, okay, I'll start from this. Usually I find these proofs where you have this two threads of logic, one absurd and one correct. I find them very confusing because we actually know that one of the threads is redundant, right? So that kind of makes me object to I mean, okay, so that initially made me object to thinking of this as structure versus randomness because we know which thread we're really in. But after kind of your talk evolved, I found it more compelling and interesting, but it's very different from combinatoric settings where the combinatorial object can actually have some structure and then be random. Whereas here, you know, it's, in the end, when we know everything, we will know that one thread was redundant. So do you think it will be, the only way in which this is relevant is that in the end proof will actually have these kinds of parallel threads in them. So do you think that's kind of a...
Well, I mean, I just wonder whether like our kind of understanding of structural randomness is just much more sophisticated in a combinatorial setting. Like we just understand it better. Yeah, I mean, there are ways that objects can be kind of somewhat structured and so on. And so that's what I was sort of hinting at, that maybe this is quite a coarse way of applying structures of randomness. And perhaps there are ways to apply it in a more sophisticated way. Yeah, I mean, along the lines of what's done in combinatorics. Yeah, I mean, it's just a possibility. I mean, I don't have like any clear ideas for how to do it, but I just think it's kind of interesting possibility to consider as kind of an approach. Yeah, does that kind of address your question?
Yeah, no, it's very, very intriguing. I mean, certainly this approach has seen spectacular results in the past decade. So yeah, even more.
Yeah, may I ask some technical question about the theorem 3?
Oh, sure.
Yeah, just about so maybe it was already asked, but R is but the lower bound is said there are no efficient propositional proofs of R. So you mean for any proof system, even extended Frege and so forth.
Yeah.
Right.
So
and R, yeah.
There is PP as R, such that for all non-uniform propositional proof systems Q, there are no efficient proofs in Q of R proof lower bound.
Oh, I see. And R must be a non-uniform.
for the unconditional result, because of the use of structure as a randomness, it has to be non-uniform. But there's kind of conditional results where you can assume kind of Root-Rich's conjecture, and then you get a uniform R for which proof conditional low bounds are hard. Yeah, but for this kind of unconditional result, yeah, because in the structure case, we only have a non-uniform system that has efficient proofs. So yeah, that's where.
Yeah, by the way, there are some works in the 2010s about a proof system with advice.
Yeah, yeah. So that's like Cook and Krajicek. Yeah. So this is sort of really that notion where you're able to use some non-uniformity in the verification of the proof. Yeah. So it's So these are kind of low bounds that are kind of like very, very strong because really we don't have like good ways of proving low bounds for such proof systems, non-uniform ones. So far, it's not been very well studied.
Any more questions? Okay, then thanks very much to Rahul, and we'll see you tomorrow for Avi Wiedersen's talk.
Oh, when is it? I mean, sort of like what time? Oh, it's at.